All right? So we just drew a curve, F versus delta x, didn't we? For our spring. So how do you find the area under a curve? You have to integrate, right? That's what an integral is. You're finding the area under a curve. In this class, we don't integrate. But if it's a simple shape, like this one, a constant force, right? We can find the area under that. That's just F times delta x. And if it's another simple shape, like a triangle, we can find the area under that, right? It's 1/2 base times height. So if we wanted to know how much work our spring did as we stretched it, we can look at the area under this curve. It's how far did we stretch it? If we stretched our spring up to, let's say, 30 centimeters, then we know the maximum force there because we know the spring constant, so we can multiply it in, kx. So this is the displacement. This is the force. And what's the area under this curve? (1/2 kx times x). 1/2 kx squared. Right? 1/2 base times height. So the work done by the spring, I'll come down here. (1/2 k x squared). It's the area under the force versus displacement curve. And this is tricky. You have to be careful. It could be positive. It could be negative. It depends which way the force is being applied to the object. Let's do a couple of examples here. Now here, let me do that. Let me draw one before this. Here's our spring. Now we compress it. Call it minus d. We let go. Let's make our surface frictionless. Okay, we let go. What's going to happen? When the spring gets to its equilibrium position, it's now the spring is pushing. When we let go, the spring is pushing the block to the right. You see that? What direction is the block moving? To the right. So the work done, what sign is it going to be? Positive. And the block speed is going to increase. When it gets to 0, the block leaves the spring, right? And keeps going. And the spring bounces back and forth a few times and ends up back at the, like it is in the top picture there. Okay, so now it leaves So if I gave you some numbers here, D is 2 meters. The spring constant is 10 newtons per meter. The mass is half a kilogram. Tell me how fast it's going. How fast is that block going when it leaves the spring? So somebody was asking me right before class, how do you know, which approach to use to solve some of these problems? So you have to look for some key words. There are certain words that go together. When you see force and distance together, you should be thinking work, right? Force and distance together work. And when you see change in kinetic energy or change in velocity leads to change in kinetic energy, you should be thinking work, because we have our work kinetic energy theorem. So those kind of all go together. Force, distance, delta K, and work. Okay, those all go together. In a couple of weeks, we'll be doing momentum problems. And we will introduce something called impulse, which is force times time. So if you see force and time and a change in momentum, those are all linked through impulse. Force, time, impulse, change in momentum are all linked together. But if you see force, distance, change in kinetic energy, or change in velocity, then you might be able to get there through the work. And that's what we're going to use in this case. The one thing you cannot use when you have a spring in your problem: kinematics equations. Okay? And before, we could maybe set up like a Newton's law problem, look at F equals ma, figure out what the acceleration was, and then use kinematics equations to find the acceleration or the final velocity, use kinematic equations to find the final velocity, right? If this was a pulley, if this, instead of a spring pushing it, there was a pulley attached with a weight, we could use Newton's laws to find the acceleration, and then kinematics equations to figure out what the speed was after it moved some distance, right? Because A was constant. But in this case, we have a spring pushing on it. So right now, with the instant you let go, the spring is pushing with a big force. There's a big acceleration on that mass, right? Because F equals ma. Big force, big acceleration. As the spring relaxes, right, as it goes back towards its natural length, the mass is getting pushed less and less and less by the spring. And at x equals 0, the force goes to 0, and it leaves the spring. So the force is changing, which means the acceleration is changing. It starts at some big value, and it goes down to 0 right at the end when it leaves, and then it stays at that speed the rest of the way. So you can't use kinematics equations. They only work for constant acceleration. So we have to have some other way of solving this. Work and energy. That's what we'll use, work and energy. Okay, so have we found how much work the spring does on the box? Because it's going to be plus or minus 1/2 kx squared, right? The work done by a spring always plus or minus 1/2 kx squared. What is it in this case? Positive or negative? We already said it, right? Positive. Because it's pushing, right? The spring force is this way, and delta x is this way, so they're both in the same direction. Positive work. K was given. X was given. X is D. I should have used D, I guess. Let me put this one as a D. Okay, so what do we get? 10 and 2 squared, right? What are our units for work? Joules, 20 joules. That's a Newton meter, 20 joules. Positive 20 joules, work done on the block by the spring. And we know that work is equal to change in kinetic energy. So that's going to be the final kinetic energy minus the initial kinetic energy. 1/2 mv final squared minus 1/2 mv initial squared. And it started from rest. So v initial was 0. So the work has to equal 1/2 mv final squared. What is m? 1/2? So that's 80. And not joules anymore. Okay, and what is the square root of 80? (8.94) meters per second.